Thanks, Marina, and thank you to the program committee for giving me the opportunity to talk to you all today. So I'll be talking about joint work with my PhD supervisor, Chris Conan, who this morning gave us a lovely introduction to Dagger category theory as a research program. And in particular, what I'll be telling you about today is a continuation of the work that he told us about in Act 4, about the axioms of the category of Hilbert spaces and bounded linear maps. And I guess I should also point out there's connections to what Paolo talked about yesterday in this limits are limits idea, but we'll see more of that shortly. But to start, I think it's worth just reminding ourselves of some of the basic objects that we're going to be talking about today. So we're going to be talking about Hilbert spaces. So Hilbert spaces are vector spaces equipped with a complete inner product, and this inner product gives them some kind of geometry. So if you take the inner product of a vector with itself, you get some kind of lengths, and the inner product between two different vectors can give you some notion of angle. Now, the maps that we're going to consider this afternoon are the linear contractions. So these are different to the bounded linear maps that Chris was talking about this morning. So the linear contractions are the linear maps that decrease length. And the categories that we're interested in are the category con of Hilbert spaces and linear contractions, and the category F-con, which is the full subcategory that's spanned by the finite-dimensional Hilbert spaces. I should also remind you what a Dagger category is, although at this point this is probably the third time this conference that you've seen the definition, so maybe it'll start sinking in. So a Dagger category is a category equipped with for each morphism f from x to y, a choice of morphism f dagger from y to x, satisfying some axioms. So the first two axioms make this dagger operation functorial in a contravariant sense, and the third axiom makes it involutive. And I guess the point in this talk is both con and f-con are Dagger categories, where the dagger is the adjoint of the bounded linear maps. So the adjoint operation is a generalization of this conjugate transpose operation on matrices, if you sort of think about finite-dimensional Hilbert spaces. So at this point, I'm ready to state, so the characterization of con, which is due to Chris and his collaborators Andre and Nesta, it's quite an involved theorem statement, which is why I'm taking a moment before I put it on the screen to say some stuff. The point here is not to get across all the individual axioms, but to give you a flavor of what kind of axioms the statement involves. Because I think what's quite remarkable about this theorem statement is there's no analytic notions involved. So there's nothing about the real numbers, there's nothing about completeness or continuity. The axioms are all category theoretic in nature. Let me bring it onto the slide. So it says that a dagger rig category is equivalent to con if and only if it satisfies some axioms. Chris told you this morning about dagger monoidal categories. So a dagger rig category is a dagger category equipped with two monoidal products, in this case, that are compatible with the dagger in the appropriate way and compatible with each other. And as you can see, the axioms are of a category theoretic flavor. So things like an object is initial, things like things being kernels, and these dagger, but also with the compatibility with the dagger, I guess, is the part that maybe is less familiar to the people in this audience. So this is the axioms of the category of Hilbert spaces and contractions. And today, we're going to build to a similar characterization of the category of finite-dimensional Hilbert spaces and contractions. Now, you might be wondering, well, if we can characterize all Hilbert spaces and contractions, then surely the finite-dimensional case is fairly straightforward. I mean, finite-dimensional things are easier than infinite-dimensional things. And I guess the point of the next part of my talk is to convince you that this isn't the case. And so, but really to do this, I need to tell you a little bit about how this equivalence that's claimed here is constructed. So let me do that. So let's start by just trying to understand how we might recover the structure of a Hilbert space from the category con itself. So within con, we have a special Hilbert space, which is the monoidal unit here. It's the complex numbers regarded as a Hilbert space over itself. And if we look at the contractions from C to some arbitrary object x, there's a bijection between these and the vectors in x of length less than or equal to 1. So the bijection is pretty easy to construct. So in one way, we just evaluate our maps at 1, and in the other direction, we take a vector x and we send it to the map that scales x by complex numbers. We could play a similar game where we replace x with the complex numbers itself, and in this case we recover the complex numbers of modulus less than or equal to 1. And so if you combine these two things, you can reconstruct x. So x is a set of all fractions, so x being a vector in x of length less than or equal to 1, and a being a complex number of modulus less than or equal to 1. So if we take all of these fractions, you can recover all of the vectors in x. So this is the idea behind the construction that will allow us to construct from our abstract category D that was in the axioms before, a new category C, which should correspond to the category of Hilbert spaces and bounded linear maps. And here, the HOMs from the special object C to arbitrary objects are actually going to give you the Hilbert spaces. So how does this work? So in the abstract setting, we have the monoidal unit I, which is going to play the role of C on the previous slide. And we're going to construct our new category C from D, so D was a category that satisfied the axioms, by formally inverting the non-zero scalars. Now this process of formal inversion I'm not going to explicitly write up on the slide, but essentially it's like constructing the field of fractions of an integral domain. And so the result, once we get this category C, we can prove, using the axioms that I haven't told you about, that the scalars in this new category C form an involutive field. So that's a field equipped with an involution. So it's an anti-automorphism, so it sort of is going to change the order of the multiplication. And I mean, essentially it's like a dagger, but for a field. And CIX is what's called an orthomodulus space over CII. So an orthomodulus space, it's a vector space equipped with a Hermitian form. So the Hermitian form here is derived from the dagger. So you take an element y and then you compose it with the dagger of an element x. And the orthomodularity condition is some condition about the closed subspaces being orthocomplemented, something like that. So it's not so important for the talk. So we get that CII is an involutive field, each CIX is an orthomodulus space. So we're almost to the point where we can say that CII is ROC and CIX is a Hilbert space, but not quite. So the key ingredient that lets us do the final step is what Chris told us about this morning, and that's this Solaire's theorem. So Solaire's theorem says that if you have an orthomodulus space over an involutive field, and it has an orthonormal sequence, so an infinite orthonormal set, then the orthomodulus space is actually a Hilbert space over ROC. Note that, so Solaire actually did involutive division ring and had the quaternions added there, but when we're considering commutative, we can't get the quaternions. So anyway, so this is a slightly specialized version of Solaire's theorem. And the point is that, well, in our abstract category, we can actually construct one of these orthomodulus spaces with an infinite orthonormal sequence. So we can construct this object that I'm writing as I to the O plus n. So I to the O plus n is this abstract analog of L2, so the space of square summable sequences. And we can construct it from the finite dagger biproducts using the directed colimit. So if you do this, you can show that Ci I to the O plus n is, well, it's an orthomodulus space, like I said on the previous slide, but it has this infinite orthonormal sequence. And so when you apply Solaire's theorem, you get out of it the fact that the scalars are ROC, and that this orthomodulus space is a Hilbert space. So that's sort of an idea of how the proof goes. So now we have our Hilbert spaces, and then, I mean, it's not so hard then to prove that the maps are the bounded linear maps, and then you sort of see that the category you started in sort of embeds into here, and you try and identify the maps in the category that you started with the contractions. But if we want to do finite-dimensional Hilbert spaces, I think it should be clear now what the problem is. And that is that we can't actually construct this object I to the O plus n, because it shouldn't exist within the category of finite-dimensional Hilbert spaces. So if we don't have an orthomodular space with an infinite orthonormal sequence, we can't apply Solaire's theorem. So we need a different approach to prove that the scalars are R or C. And so that's essentially the main topic of this presentation. It's coming up with a conceptual proof. So I say conceptual here also because Solaire's theorem is a bit of a black box. If you look at the proof, it doesn't give you much intuition for why. I mean, there's a lot of messing around with sequences within the space, and it doesn't give you a feeling for where the completeness comes from. So what we want is a conceptual proof that the scalars are the real or complex numbers that doesn't use infinite dimensionality. And so if we have that, then we can go the next step and give axioms for the category of finite dimensional spaces. Okay, so how do we do this? Well, I'm going to focus first on the part of the axioms where the completeness is really coming from. So, and that's the directed colimits, but actually we really only need to consider the colimits of omega chains, which in this talk I'm going to call sequential colimits. So it turns out that con has sequential colimits. So if I have a sequential diagram like so, then we have some colimit like this. And I'm not going to tell you exactly what the sequential colimit is. If you want the concrete description, you can go and look at the preprint. But I will tell you some interesting things about it that should also link back to what Paolo was saying yesterday about this connection between limits in category theory and limits in an analytic sense. So first, let's just consider a vector x in x1 and look at where it goes within this sequential diagram. So we have x, we have f1 of x, we have f2 of f1 of x, and so on. And because the morphisms in the diagram are contractions, we know that the lengths of these vectors in this sequence are decreasing. So we have a decreasing sequence of positive scalars, and whenever we have such a sequence, we know that it has an infimum. It's a bounded decreasing sequence. It has a limit, and the infimum and the limit coincide. So what's actually particularly nice is that this infimum and this limit are recovered in the colimit object. If we look at where x is sent to by this J1, the length of that vector is this infimum, or this limit. So this is how the colimit object is encoding infima of decreasing sequences of positive scalars. And so, I mean, the main idea of this talk is that perhaps we can reverse engineer this so that we can recover infima of decreasing sequences of positive scalars from the colimit in the abstract setting, and then use this to realize the fact that actually what we have is either R or C. So that's what we're going to do. We're going to turn these observations about con into definitions about D and C. So how do we do this? Okay, so the setting we're in is still with the axioms for con that I showed you on the previous slide. So we're not up to doing finite dimensional stuff yet, but what we're going to do will also apply in the finite dimensional setting. So we're going to suppose that D satisfies those axioms, and we're also going to consider the scalar localization of D. So this category C that I constructed by inverting the non-zero scalars. Now we're going to consider this set P of scalars which are of the form x dagger x, where x is a morphism from I to some object x. So these are morally the positive scalars, and you can show using the axioms that P actually forms what's called a strict semifield. So a strict semifield is essentially like a field but without negatives. The strict meaning it actually doesn't have negatives. And then the next step is we're going to define a partial order on P, where we say that a positive scalar x is greater than or equal to a positive scalar y if there's some contraction, sorry, I say contraction, but so morally D is a category of contractions and C is a category of arbitrary maps. So if there's some morphism in D that maps x to y. Because if you think about, if we really want D to become the category of contractions, then applying a contraction to some vector should result in a vector that's shorter. So this is why this inequality makes sense. Now, of course, you might wonder, well, okay, there could be multiple vectors that represent the same positive scalar. So there's something you have to do here to show that this partial order is well defined. And to do that, you really need to actually go and delve into the axioms, which I didn't tell you about. But if you're interested, you can obviously, if you go and look at the preprint, it's all worked out there. So you can take my word for it that this partial order is well defined and is actually compatible with the semi-field addition and with like conjugating in the sense of like multiplication by, say, R and R dag on both sides. So it's compatible with the semi-field and the dagger in a way that makes sense. Okay, so we have a notion of positive scalars, we have an ordering, and so the next step is we want to show that we have infima of decreasing sequences of positive scalars. So how does this work? Well, let's start with the decreasing sequence of positive scalars. So I'm going to use red to denote morphisms in C, and blue will denote morphisms in D, so that in the picture you can keep the distinction. So this looks like a diagram like so. So we have x1, x2, these are morphisms in C, and the inequality is realized by these contractions that make the triangles commute. Now what I haven't told you is why I can assume that these morphisms are epi. That comes from this epi-dagger monofactorization that you get from the existence of dagger equalizers, dagger kernels. But anyway, you can assume without loss of generality that these morphisms are epi. Okay, so now we have a sequential diagram of contractions, a sequential diagram of morphisms in D, and because D has co-limits of sequential diagrams, we can consider the co-limit object here and the co-limit cocone. And then you can ask, well, we have these morphisms J1, X1, J2, X2, and so on. And you can actually show that they're all equal to each other. So we get this morphism X, which is equal to these composites. And so the claim is that X dagger X is actually the infimum of these positive scalars with respect to the partial order that I defined. And how this works is, well, if I have some other positive scalar that's less than or equal to everything in the sequence, I'm going to get, from that scalar, the contractions realizing those inequalities are going to form another cocone on this sequential diagram. Then you use universality of the co-limit cocone to get a contraction that realizes the fact that that scalar is actually less than or equal to X dagger X. So I think this is really nice the way it works out. Like, it's just quite satisfying, and it really tells you where some kind of completeness within the semi-field is coming from this existence of sequential co-limits. Okay, so now we've done that, what we have is we know that P is a partially ordered strict semi-field that has infima of bounded decreasing sequences. So from that, somehow we want to deduce that actually the field of scalars is either R or C. So there's this theorem by Demar that says that every partially ordered field that has infima of bounded decreasing sequences is isomorphic to R. And so this is a variant on various classic results about partially ordered fields. The most challenging part of this work was actually connecting the dots. So going from this partially ordered semi-field, that's complete in this sense, to showing that the partially ordered field is complete. This took a lot of work. I think we almost had a finished paper and then realized we had a mistake and we had to come up with a different way of doing it. Like, this part took most of the time in this work, but there's also something that I'm not going to talk about today because I just don't have enough time for that. Okay, so at this point, going back to the characterization of Con, we now know how to show that the scalars are R or C without relying on the existence of this infinite dimensional object. Now I've highlighted this axiom 9 because axiom 9 is really the only problematic axiom for Fcon. Another way of saying that is Fcon, finite-dimensional Hilbert spaces and contractions, satisfies axioms 1 through 8. There's axiom 9 that's not satisfied by Fcon. So somehow, I mean, and I'm going to explain in a minute, but somehow, like, for axiomatizing Fcon, we need to strike some balance between asking for enough co-limits that we can prove that the scalars are R or C, but not so many co-limits that we can construct infinite dimensional spaces. So I should say, it's this diagrams like this one that are the problematic ones. So if I have complex numbers injecting into the first coordinate of pairs, injecting into the first 2 coordinates of triples and so on, then this diagram here doesn't have a co-limit in Fcon, and in Con its co-limit is L2, the space of square summable sequences. So it's diagrams like this that are problematic. So the solution is this notion of bounded diagram. So we say a diagram is bounded if it admits a co-cone of monomorphisms. And the point is that Fcon has co-limits of bounded sequential diagrams, and moreover we can sort of modify the proof that I gave earlier in the talk to be able to use just co-limits of bounded diagrams to prove that the scalars are R or C. So the final ingredient we need is a way to ensure there's no extraneous objects in our category that happen to not be finite dimensional. So we have this notion, I mean, I guess there's various ways of characterizing finite dimensionality, but this is the one that was that fit most easily with the rest of the axioms. So an object X is dagger finite if f dagger f equals 1 implies ff dagger equals 1 for all morphisms f from X to X. This is some dagger analog of Dedekind finiteness, where you say that every, say, injective function on a set is, so if every injective function on a set is a bijection, then it's finite. I probably messed that up, but anyway, the idea is there. So this is the dagger analog of that. An object in Con is dagger finite if and only if it's finite dimensional, so it really does capture finite dimensionality. And so with that, we now have our characterization of Fcon. So I've replaced the old axiom 9 with new 9 and 10. So 9 says every bounded sequential diagram has a co-limit, and 10 says every object is dagger finite. And that's the end of my talk. So if you're interested in more, there's a preprint on arXiv, which you're welcome to read. There's also a post on the N Category Cafe, which sort of goes into a bit of how we sort of went about, how did we arrive at this idea and some of the twists and turns along the way. But yeah, thank you for your attention.
Maybe a comment. So the fact that there's this limits both here and in my talk is like coincidence. Actually, we used some of their results to prove ours.
Thanks.
How far are you with characterizing finite-dimensional Hilbert spaces and linear maps?
So the ideas from this talk also work in that setting. We haven't put a paper out on that yet because, I mean, we've actually gone down a rabbit hole and have been thinking about Hilbert modules and C-star algebras and things, and I think the plan is to fit that into that paper as like a thing on the side. Because I think having, I mean, the main ideas behind doing that are essentially the same kinds of ideas that are already in this paper. But yeah.
And what do you say about C-star algebras?
Not necessarily ready to talk about that yet, but essentially we're working towards, so in the axioms for Hilbert spaces, which Chris talked about this morning, if you remove the simplicity assumption on the object that generates the scalars, the question is what kind of categories do you get? And you get something like some special kind of not all Hilbert modules over all C-star algebras, but something in that setting. But yeah, I'm not ready to talk about that at the moment. Thanks.
So I appreciate Chris's point about honouring our predecessors, you know, in his talk. But in science, we honour our predecessors by dismantling their work and rebuilding it in a new setting. So I wonder what progress is being made in opening the black box theory.
Oh, that's an interesting question. So, like, you're wondering whether using ideas from here, we might be able to come up with a nicer proof of Solaire's theorem. It definitely has crossed my mind, but I haven't put much effort into trying to actually make that a thing. But it's quite possible that some of these ideas could be relevant. I think you're right.
I'm trying to ask Chris that question.
So, yeah, I don't have anything to say this time, and but it's definitely possible that something could be done along those lines.
Two last questions.
How constructed is the last term and your approaching strings, and then if it's not, then
I'll be honest, I haven't really thought along these lines. Don't know whether it's necessarily relevant, but to be able to recover all of the category of Hilbert spaces, there is some kind of axiom of choice thing going on. But I guess if you didn't want to do that, you could say, well, we want to recover all Hilbert spaces with an orthonormal basis or something like that. But yeah, it's definitely not my area of specialty.
You have four basic things about constructive reasoning.
Last question, Clémence.
in linear algebra over any field, I think there is this easy characterization of finite-dimensional vector spaces by saying that the double dualization map is an isomorphism.
Mm-hmm.
Is there something similar in the Hilbert setting that you could recover finite-dimensional Hilbert spaces from some kind of double dualization map?
So I haven't thought about the double dualization version, but I think a very similar kind of characterization is to say that an object is dualizable in, like, so if you're in a monoidal category, you can talk about dualizable objects. So that works in the category of Hilbert spaces and all bounded linear maps. And when you go to linear contractions, the finite dimensional spaces aren't dualizable in that sense, for the reason that the morphisms that implement the adjunction, they're not, well, at least one of them, maybe both of them, they're not contractions. So that doesn't work. However, we did come up with some weak notion of being dualizable that would work in this setting, and which, when you so that applies to the category D, such that when you look in the category C, you actually have these things be dualizable in the actual sense. So you can do that, and I think we had something where that would be sort of, given some of the other axioms, equivalent to dagger finiteness, which is the thing that I had. But in the end, it just ended up being a bit too messy to be bothered including it in the actual paper. And I think when we finally get around to doing the Hilbert spaces and bounded linear maps one, which I was talking about before, we would try and include some kind of result like that to give a few alternative characterizations of finite dimensional things. But yes, that's a good question. Thanks.
Many thanks again.